take your time on the midterms because the level of difficulty should be about the same as the homework, or if not more easier than the homework. The difficulty level should be around that level. Okay? So, anyone has any questions before I start? No? All right. So, let's work on some problem that's related to LQ, but this concept is much more, I like this concept a lot. It's integrating many things into something we know already. And we will see. I mentioned this in one of the lectures before. How we mentioned LQ is time domain design, about state space design. We have cost functions, quadratic cost functions. And I mentioned once, in this state space design, how can we integrate some of the loop shaping ideas into here, like frequency domain cost functions. And I mentioned this concept is very useful, how to integrate this frequency domain design idea into time domain. You'll find a lot more applications, not just in this particular example, but there are more applications of this concept. So the central result for building up this connection is Parseval's theorem. We'll talk about some of the background of this theorem, and then you will see it's very intuitive to understand. And then after that, we'll do frequency domain, frequency-shaped LQ. This is called FSLQ, frequency-shaped LQ problem. And you'll see this can be translated to the standard LQ problem, which we can solve very easily. The big picture is like this. You know now, I asked you before in one of the lectures, I said, in LQ problem, you see it's optimal control. The design parameters are Q, R, these weighing matrices in the cost function. Okay? So in ME232, there are some guidelines for selecting Q and R. But you can see now, if they are just constant matrices, we don't have, you might think being constant matrices might not be the best way in practice. So you might think whether I can make this Q and R time dependent or something else dependent on other parameters. And this FSLQ is exactly doing this, introducing more design freedom for Q and R. Okay? Whenever you see some integration of quadratic functions, you can think about the meaning of that. For example, the integration, look at here. This integration, you see, what's the intuitive meaning of this integration here? If, let's say, ft is it's a time domain signal, what would be, let's see, if ft is a current, if ft is the current in the circuit, integration of the square of the current, what's that? It's approximately an energy, but there might be some scalings to make it the true energy function. But you see, this is an energy function. Now, this theorem called Parseval's theorem, this guy, this is a French mathematician. He invented this in the year of 1970s or something. 17, yeah, he invented this very early, in the 17th century, between 17th century and 18th century. So he showed that the integration of a square, so f transpose times f, approximately the square of this f time domain signal, equals exactly some normalized form of the integration in the frequency domain. Okay, this is again a square root, a squared quadratic function. And this f is the, not mentioned here, this f is the Fourier transform of ft. Intuitively, this just means for the one-dimensional case, you already see that the energy in the time domain equals the energy in the frequency domain. Okay? And here, just a little bit more details. If ft is defined on between 0 and infinity, ft is called causal. If in this case, ft is called causal, meaning ft is causal. Okay. In the general case, ft can be defined from negative infinity to positive infinity as well. So in that case, this integration is whatever region that ft is defined over upon. Okay. And in the discrete time version, replace the integration sign with this summation sign. Everything else is the same. So Passivo, I mentioned, he published this in the 17th, between the 17th and 18th century. Actually, if you look, I checked from Wikipedia, he published just 5 publications in his entire academic career. But these 5 publications are extremely important. And it's something we have been using again and again in engineering nowadays. Okay. Now, let's work on this cost function here. Now you have seen this LQ cost function. If I apply the Passivo theorem, then you see integration from 0 to infinity x transpose t q xt dt equals nothing but 1 divided by 2 pi, negative infinity to positive infinity, then x negative j omega transpose q x j omega d omega. Okay? Now you see some intuitions come up now here. You don't see much intuition of how to make Q, for example, time dependent here. But you can get more intuition here. You can make this Q to be frequency dependent. Okay? For example, let me ask you, if X contains a lot of low frequency component, what should I choose for Q to better minimize this quadratic cost function? If X contains a lot of low frequency component. Should Q be, let me give you some choices. High pass. Should Q be something like this, if this is frequency, or something like this? High pass. Can you explain why is it high pass? That's one explanation. So think about it a little bit more. It's actually the contrary case. If X contains many low frequency components and we want to minimize this quadratic cost, Q should actually be a low pass. So the intuition there is that if the low frequency component makes a lot of weight in the cost function, then I should emphasize to minimize this part of the frequency component. So if you choose, for example, if you choose the low pass, if you choose this way, that means, okay, I want to focus on the high frequency region. The low frequency errors doesn't make much count in this case. Make sense? So now you see, immediately we are exactly building the frequency domain design intuitions in this cost function. So in a more general example, if the spectral density of X looks like this, and we want to focus on this frequency range, then we can choose Q approximately as a bandpass filter in that case. You can do it something like this. So the intuition behind is that for whatever frequency region that we want to have more enhanced control, we just make the Q to have a little bit more higher gain in this frequency range. Okay? So that's for the Q. Think about what will be the case for R. For example, if the system has a lot of high frequency measurement noise, what should R be selected? Take a moment to think about this. We'll visit this very soon. Okay? So now, you have seen the intuitions. Now, because of the Parseval's theorem, we can expand the design freedom by making Q to be frequency dependent in this new cost function in the frequency domain. So keep in mind, we are now designing in the frequency domain now. The intuition works very well, but there's one challenge at the moment because we don't know how to solve this. We didn't learn what's the control law to minimize this quadratic function in the frequency domain. We only learned how to do this, didn't learn how to do that. So the key steps in frequency-shaped FSLQ is to do these following steps. So it's about how we can translate this equation 4 which is in the frequency domain. How we can translate this into the time domain to this equation here. So that's the goal of this slide. Okay? So we have, let me rewrite it here. J equal to 1 divided by 2 pi, negative infinity, then x negative j omega, transpose q j omega, x j omega. So something related to u, then d omega. Okay, so the key step is this. Break q as the combination of qf transpose times qf. So in this way, we can define a new frequency domain, xf, which is x passed through this filter qf. Okay? In this way, we can get this guy. We can translate from this equation 4, this is equation 4, to this new function here. And then, if you see this, do once again the Parseval's theorem. So we can translate from this frequency domain, energy type of function, again, back into the time domain, quadratic function of x, f. Okay? So that's for the case of x. Exactly the same thing can be done for the u. Now I will write it, the complete equation for u. Do exactly the same thing. First of all, break R into a quadratic term of RF, and then introduce this new filtered control signal UF. Then you can achieve this product term UF transpose times UF. Then do again Parseval's theorem to arrive at this cost function. Okay? So that's the intuition. Now, you can see this guy. Now, for the remainder part of the lectures, I'm just going to show you how this new LQ problem can be translated into a standard LQ problem, which we can know how to solve. Okay? Now, summarizing, we have the plant, a state space plant, ABC matrices, and the new cost function. And we have this filtered state and filtered input, filtered control. What should we do? Intuitively, what should we do to translate this problem into a standard LQ problem? Look at this one. You see, XF is not yet a state of the system. So what we need to do is to think about how to expand, enlarge this plant to include XF as a state of the plant, okay, and include UF as some sort of control inside. Okay, so let me start with the first part, this filtered state. Okay. The first thing to recognize is that this is usually this is a multiple input, multiple output system, because the state X can be a dimension of n by 1. And this filtered state, depending on how you design it, let's say the dimension is q by 1. Okay, so QF is usually a multiple input, multiple output system. Write the transfer function. Suppose we design QF such that it has a transfer function that looks like this. Okay? Write it in a state space form, whose state is C1, whose output is XF. Okay? If, let's say, if the order of QF is, let me see, let's say N1. What are the dimensions of the A1, B1, C1, D1 matrices? This is a question. And the dimension of X is n by 1. The dimension of XF is q by 1. What are these dimensions here? What about X1? What's the dimension of X1? N1 by N1, right? This one is easier. What you need to pay attention to when you do actual design is the dimension of B1, C1. What's the dimension of B1? So it has to have the same rows as A1. How many columns should B1 have? It should be the dimension of X. So it should be, let's see, n, because dimension of X is n. What about C1? XF has q rows, so C1 should have q rows. And the columns of C1 should match the dimension of D1, so it's q times n1. And finally, D1 should have the same columns as XF, so it's q by, and then here, same columns as the dimension of X, so it's q by n. Okay? So keep this on your notes, because it's going to be handy when you do the homework, the next homework. You have a design problem for this. We have mentioned QF is the state filter. We designed this one, and it can be selected to meet the desired control action. We have explained if XF, if we want to focus on low frequency error rejection, QF can be a low pass filter. You will have some design examples to do this very soon. So exactly the same thing for the input filter. Now let me ask you, let's come back to the question. If you if the system has a lot of measurement noise, high frequency measurement noise, what should RF be selected as? High frequency, high pass filter, right? Exactly the case. What about, let's go into some more details even. You know, for whatever kind of high pass filter, let's say it looks like this. You got to select the low frequency gain and the high frequency gain. In this case, what's one inconvenient design to select the low frequency gain of RF? 0 dB. That should be a little bit more easier to design. So instead of making this 0 dB, this is more convenient to design because we know how to, because conventionally, yeah, I should take this, I should explain it a little bit more carefully. We should make, let's do this. So we know how to design, it's usually very convenient, it's very easy to design constant R matrix. Now, when you go from constant R matrix to RF, one convenient design is to make R to be a scalar, make RF to be a scalar R times something that looks like this. Because let's do a single input, single output example. If in the original LQ problem, we choose R as, for example, 10. And then someone came to you and said, 10 has the disadvantage that the high frequency component of U is not handled well. How do you go from this 10 design to something that's more flexible? And what I said is one way to do this is to make this RF to be 10 times something that looks like this. That's all I'm saying. Make sense? All right. Now, you can do the same thing about the dimensions of A2, B2, C2, D2. In this time, I won't do it all over again. I'll just ask you, if U is, let's see, I didn't say what's the dimension of U. So let me just say, U is NU dimension, and UF is NUF. The easiest way to check whether your design is correct is to check the dimension of D2. D2, the dimension of D2 should be NUF times NU. Okay? So make sure you check the dimensions, and this is something that has to be true. Okay? So in summary, we have now, let me write the results we have obtained. In summary, we have, for the state filter, XF, we have Z1 dot equals A1 Z1 plus B1 X. And then XF equals C1 Z1 plus D1 X. And then we have the filter for UF. We have also the plant, the original plant, X dot equals AX plus BU. Y equals CX. Okay? So tell me, what should I do now to solve this J equal to integration from 0 to infinity XF transpose XF plus rho UF. What should I do to, should be plus. What should I do to solve, to be able to solve this new LQ problem? What should we do now to be able to solve this? This is something very common in optimal control. We'll be actually using this concept again and again very soon. Now, you see, in a standard LQ problem, this should be the state of the system. Okay? Now, after we have done all these augmentations of x and u, what is the, for example, what's the order of the enlarged system now? If we have this all together, and the dimension of this is, I used n1, I think. So z1 is a n1 dimensional vector. And let's say z2 is a n2 dimensional vector. What should be the overall order of the dynamics over here? If x is nth order, the total dimension should be n plus n1 plus n2. Okay? Now, this should be the actual enlarged state. Let's say xe, yes. So let's call the enlarged state vector of the system should be xe. What you want to do is to translate this guy into some quadratic function of the enlarged state. Okay? Where xe should contain all the dynamics of this enlarged system, x, z1, z2. So that's the general goal we're going to achieve. So if you understand that, the remaining steps are pretty standard. So we are going to now combine these three dynamic systems into one. So let's do that very quickly. So we got to be able to explain x, z1, z2 in this sort of state space equations. So the input to the system is still u, but it has these states. And the output, we'll work on the output later. Let's work on this state space equation first. So we got to do, for example, for the first case, the dynamics of x. This one is the most easy to do, I think. It's going to be x dot equals ax plus bu. Doesn't depend on z1 and z2. And then z1 dot is a1 z1 plus b1 times x. z1 doesn't depend on u. And then z2 dot, look at this guy. z2 dot is going to be a2 plus b2u. And it doesn't depend on x or z. Okay? So this is the enlarged state. And these are the matrices, equivalent A and B matrices for this enlarged space system. Now, with this, what is xf in this case? Write xf as a function of this state, this enlarged state. What should be the matrix ahead of it? If I give you all this information here. xf should be 0, and then what? C1, look at this guy, right? D1, right? 0. And then nothing here. 0 times u. So let's call this CE. So Now you see, we can conveniently express the first term. What about UF? UF is somewhere here. What's the matrix here? UF is C2 times C2. Doesn't depend on X, doesn't depend on Z1, but it depends on U. Okay? So let me see if I have a name for this. I didn't give a name for this matrix, so let's keep it for now. In summary, we have obtained this. The enlarged state space system with new expressions of XF and UF. So now, you can easily see that XF transpose times XF is going to be, because XF equals CE times XE. So now you can get this first term. Then the second term would be, I have to do a little calculation here. So look at the second term, UF transpose times UF. We have expressed UF as a function of the state, which the result is 0, 0, C2 XE plus D2U. So put it here. We're going to get this guy equals, first of all, XE transpose T. Then this guy inside. Let me double check whether I need this. Okay, let me see. 0, 0, C2 transpose plus D2 transpose plus U transpose D2 transpose whole thing times 0, 0, C2 XE plus D2U. Okay? Let's see if I have any typos. Looks fine to me. Okay. Now, let's expand this. I'm going to get XE transpose T. Then I'm going to have a quadratic term. I'm going to have a quadratic term about XE. What are the matrix dimensions here? I'm going to get 0, 0, 0, 0, C2 transpose C2. And then all the other terms are 0. Then I'm going to get a cross product term between XE and U, which is going to be 2 times, let me see which order I choose. I'm going to choose U to be going first. So U transpose T, D2 transpose times, don't have enough space, times 0, 0, C2, XE, T. And then I'm going to have finally a quadratic term of U, U transpose T, D2 transpose, D2 UT. Okay? Just algebra, matrix algebra. So now, let me go back. Let's come back to here. With this result, I'm going to get this. Over here, I'm going to have this guy equals to XE transpose CE transpose CE. This is the first term. XE plus this second quadratic XE transpose this matrix here, XE. Then plus these terms, these two extra terms, which are written here, 2UT times D2 transpose times this guy, which is exactly here, D2 transpose times C2. Then there's a scaling of rho here. And over here, I'm going to have D2 transpose D2, and then times the scaling factor rho here. Okay? So on the current version of the nodes, there's a typo in the sense that this should be QE should be this guy plus 0, 0, 0, 0, 0, 0, 0, 0, C2 transpose C2. Okay? So QE equals CE transpose CE because of the derivation here. QE equals CE transpose CE plus this matrix here. So that's the typo on this line here. The result, this result is still correct. Okay? So now we have a general expression of LQ problem. You see, the general expression of this LQ looks like 0 to infinity XE transpose QE XE plus 2U transpose T NE XE T plus U transpose T RE UT. If you recall homework number 1, I think, you remember doing a discrete time version of something that looks like this, the optimal tracking problem, and you used dynamic programming to solve that problem. So you know it has an optimal solution. So as a matter of fact, the optimal solution looks like this guy. It's still a state feedback optimal control law. So we're using the state XE here, and we have an algebraic Riccati equation. So in this, in the remainder of the lecture, I am going to explain how this solution is obtained using not LQ, not dynamic programming, but something else. Okay, but the intuition is still pretty obvious. We're still having a state feedback gain, where the matrices in the state feedback gain comes from a Riccati equation. So I want to do a little bit extension to give you this solution of general LQ problems, where I have this general quadratic function of x and u with a cross product term. So that's the only difference here compared to a standard LQ. Okay, we're going to assume general controllability and observability conditions. And I'll show you that the solution of the problem is given by these two equations. Okay, so let me ask you first, if AB is controllable and the full state are accessible, is this x, can we control x to be 0, to reach to 0, if AB is controllable, right? So guaranteed, if AB is controllable, then we know for sure we can have some design to make the system asymptotically stable, all right? If you get this idea, then you will have no problem understanding this part. So we have no problem to drive xt to 0. Consider this Lyapunov candidate function, which is, you might see the structure is very similar to what you have seen in state feedback control designs. So I'm going to do x transpose t times p times x. Then if you see that in the end v infinity is going to be equal to 0, because we can have some design that will drive this x to be 0. Consider this kind of fact that if I do v infinity, if I consider v infinity minus v0 to be this integration of v dot from 0 to infinity, okay? I can do this very easily. Then I'm going to get integration from 0 to infinity. V dot is going to be x dot transpose t p times x t plus x transpose t p x dot t. Okay? So it's actually from this, if you see this, you can actually get a little bit more intuition of how the Riccati equation comes from. What's x dot of t in this case? I have assumed that x dot equals ax plus bu. Okay, so put this here. Then you see I'm going to have a transpose times p term from this guy. And then over here, I'm going to have something related to p times a term coming from this guy. So remember, either you do a Lyapunov equation or do a Riccati equation, you have this term, a transpose p plus p a plus something else. Okay? So from here, you'll very soon see the Riccati equation will very immediately appear here. So let me complete the writing here. I'm going to have x transpose t, a transpose plus u transpose b transpose px plus x transpose t p ax plus bu dt. Combine the terms, you're going to get x transpose t a transpose times p plus p times a xt. And then the cross product term between x and u, I'm going to have u transpose b transpose p xt plus x transpose p times bu, which is the same. So I'm going to get 2 here. Okay? So here, if you do this step, then you see we are having something that looks very similar to a Riccati equation structure. Now, do this extra look at this original cost function. Look at this original cost function. If you want to achieve something that looks like this, a transpose p plus pa, we have it here. What do you think we need to do an extra step to introduce something related to q in this quadratic cost of x? In other words, how can we, it's hard to explain, how can we make use of this result here, that negative v, so it's v infinity minus v0 equals this guy. And you have seen that v infinity is 0. And x0, v0 is x transpose 0 p x 0. what would be some possible ways to combine these two equations? If I tell you V is some kind of Lyapunov function, some kind of energy of the system. Let me give you one hint. What is the optimal cost, J optimal? Everyone sees that? J optimal is exactly V0, right? So do this, let me put back here. You know that J optimal is V0 after you learned LQ, all right? So do this, add these two systems, add these two equations together. So you're going to get J, assume this is optimal. J, assume we are reaching the optimal using some U. On the left-hand side, we have this. And on the right-hand side, we have integration from 0 to infinity, x transpose t. Inside, I'm going to have A transpose P plus PA. Then I have another quadratic term of x. So I should get Q here. Then I have plus 2, so it's this term, U transpose B transpose P plus this N matrix here, X T, then plus U transpose T R U T dt. Okay? And you know it equals to 0. So now, look at the right-hand side. It's a quadratic function of x and u. Okay? We just need to now think about what would be the control u that will minimize this quadratic function. If I ask you, how do we solve intuition? If I ask you, how can we minimize x squared plus, let's see, x plus let me think about this example. Plus x times u plus u squared. If I ask you how to minimize this guy, x and u are the decision variables here. Take the partial derivatives with respect to each term. You can get the results, right? Let me go one step further. What you are actually doing is to write x squared plus xu. What we are actually doing, if you see the result, is going to be this. Four, 3. We're actually minimizing this, right? So this guy equals this guy. We're actually minimizing the summation of two squared terms. So if you recognize this fact, you immediately see the relationship between the optimal u and x has to be that x optimal has to be equal to -1 divided by 2, u optimal. So this is equivalent to saying u optimal has to be 2x, -2x optimal. Okay? So let me verify this and see whether this is the case. So if you just take the partial derivative of these guys, what you're going to get. Let me call this f. Partial f, partial x equals to 2x plus u, right? We want it to be 0. You see, immediately, this has to hold. Okay? So if you think about this very simple example, what you actually do in this minimization, in minimizing whatever quadratic functions, what you actually do is minimizing this summation of squared terms. As long as you can break it into this form, then you will know immediately what kind of u you're going to need. If you take the derivative, let's take a look. You're going to get 2u plus x it depends on, let's see, if you see, let this to be 0. If you solve from here and get u equal to negative 2x, and then put this back here, what you're going to get is f as a function of x. All right? So here you are thinking that x is the state. Actually, someone asked you, some of you did this homework number 1 and asked me about this. When you take the derivatives with respect to u or x in the first homework, I think you asked this, right? And you did the other way, taking the derivative with respect to the other term and arrived at the same conclusion, right? So let's think about this into more for some more details here. If I take a look at this guy, so your proposal, we're going to get a different relationship between u and x. So let me do one more step and see where we're going to go beyond this. So I'm going to have f equals x plus 1 divided by 2 square plus 3, 4 u square. And we want to minimize this. If I regard x as the state variable, so if I set this to 0 to get u equal to negative 2x, and then I plug this inside here, I'm going to get 3 divided by 4 u squared, which is 4x squared, equals 3x squared. If I do the other way around, f equal to, if I do partial f, partial u equal to 0, Not what? Yeah, here it's coupled. Yes. So here, it's actually it actually totally depends on which variable we regard as the input, as a control variable, and which one we regard as the state here. And this guy, let me take a moment to look at this. See if, hold on, let me see. Okay, we have some time. Let's look at this all together. If you have any, if you find anything, you can feel free to let me know also. So indeed, if I do this, I'm regarding U as the thing inside. So in the end, I'm going to have F U equal to something, right? F U optimal equal to something. Let's see. I got X, then put it inside. I am going to get, huh? Oh, so you already calculated. I'm just thinking. Yeah, I kind of feel it's going to achieve the same result. So let's see. Huh? Yeah, I'm thinking I'm going to get the same thing. So let's finish this. 4, 3, X, no, not X. I'm going to express it as U, so I'm going to get X is 2U, 2U. Plus U optimal square. Hmm? Yeah, let's do. Yeah, I made a mistake here. Should be 2. Mm. Yeah. So I think, yeah, it totally depends on which thing you regard as the control variable here. The final form of the f is the same if you regard each one as the control variable here. Okay, so in this case, we are regarding U. We are regarding X. We are regarding X. We are regarding F as a function of X. We want to minimize. So I think the logic here, in this sense, is still valid. Mm. Yeah. Yeah, so I came up with this example randomly. What in the actual case is actually going to be something very similar but slightly different. The actual case is something actually looks like this. So maybe this random example that I thought of isn't the best way to think about it. So let me first show you what's the actual thing in the LQ problem formulation. So the actual thing is, in the end, you get this. It's a quadratic, it's a square of something that looks like this. Quadratic function of x, then quadratic function of some u plus x that looks like this. So if I think about this case, then my example might as well be x. So if I start again as this example, what I wanted to do is probably u plus this square plus this x square. And I need to go one step more further. So if I have u plus some term x, now it becomes a general, let me do the matrix case. This becomes a matrix. I'm going to have x transpose, then another matrix inside here. I want to minimize this guy. Okay? So now if we look at this, then, and we know that this integration from 0 to infinity dt. So we have explained before, this guy is 0. Okay? If we look at this now, then what you see is that this guy has to be 0. And this guy has to be 0. That's what I had originally wanted to obtain. So this form, this kind of structure, that's my original goal. So anyone has question about this part? If I have two squared, the integration of two square terms, which give me a result of 0, then inside, these guys has to be 0. No, if u equals, let's say if this matrix is K, and this guy is some matrix product, let's say M. As long as M is 0 and u equals this, then it's fine. Yeah, example, I wanted to give you some intuition, but this might not be the best example because these terms here are fixed. I want it to be changeable like this. So let's see. I really want to make this example work. If I have rho Q, no, let me put Q here. Then I'm going to have U square rho divided by 2. And then here I'm going to have, let's say, some other term which is containing Q minus 4 rho square x square. Everyone sees that? So if rho and q, think about it, not constant, you can see under the conditions that u equal to negative 2 rho times x and q equal to 4 rho square, this guy is 0. That's what I had originally wanted to achieve. And if you see that, then the general case is exactly here for the matrix case. Okay, I wanted to do this example because immediately, if you can do this, you can essentially derive Riccati equation. Okay. So anyone has any questions more on this example? If no, let's come back here. Let's come back here. So now, recall what we have achieved. We have achieved that this quadratic function, which contains not only x and u, but also some cross-product term between x and u. So this is exactly the example here. For the one-dimensional example, you have some cross-product term between x and u. So if you can express this guy as something that looks like this, integration of this plus some term about u plus x, then you will see these guys the optimal condition to reach this cost is this guy has to be 0 and this quadratic cost has to be 0. Okay? So now I'm just going to show you how to formulate this. If you have a quadratic function of u and some quadratic cross product term between u and x, what you can do is this very useful mathematic trick that 2x transpose t pb. So write these two first as r negative 1 divided by 2, r 1 divided by 2u. Okay? So write this term first as I introduce this square root of r and its inverse here. And then I can do u transpose r1 divided by 2, r1 divided by 2u. So now you see I have a squared term of u here, r square root of r times u, and it's going to occur here. If I subtract and add this term, let me do dashed line. If I add and subtract the square term of this guy, which is x transpose t pb plus n r inverse pb plus n transpose, and then x. All right? If I add and subtract this term, I'm going to get exactly r square root of r plus x transpose t pb n r inverse pb. No, I get r. So it's the square root of this term pb plus n transpose xt. So let me finish up the equation first and then explain it. X. Okay, so I have added and subtract this term, this quadratic term of x, to complete the squares. This is essentially complete the squares. Okay, I introduced a quadratic term of u and x over here. all right? So if you do that, then you see we have essentially got something in this structure, and then this guy will be combined to here. And the full expression is going to be this. You see, this square term, and then this term is going to be combined to the x term, square term of x. PB plus n R inverse, PB plus n transpose. Okay? And exactly here, you see, this guy is the left-hand side of the Riccati equation. And if you let this guy to be 0, you get exactly, so u has to be negative r negative 1 divided by 2. So letting this to be 0, you get exactly the state feedback gain for u. And this is how you can solve a general LQ problem. And you can see exactly where the Riccati equation comes from and the state feedback gain. Okay, so using this result, you can essentially, applying this result, you get exactly the solution for the FSLQ problem. You get exactly the solution like this. Okay? So any questions for this part? It's finally clearing up, or you're still confused? Okay, so if you have any questions, feel free to come to my office hour. And I will close up today's lecture by summarizing showing you the structure of the FSLQ implementation. So we have x dot equals ax plus bu, y equals cx. Okay? And then we have z2 dot equals a2 z2 plus b2 u2. We used uf equals c2 z2 plus d2 u. Let me see if this d2. Yeah. And then I have x z1 dot equals a1 z1 plus b1x xf equals c1 z1 plus d1x. Okay, so the implementation looks like this. X, this is the part for z1. X goes through b1 and then goes through si minus a1. So do the Laplace transform of this guy. Then you can get z1 equals this guy times x. So this is where the state feedback concept shows up. The actual control u, the optimal control u, is going to be a combination of the state z1 plus the combination of the original state x, something related to x. And then do the same thing here. Express, this is u. So z2 is u passing through b2, and then si minus a2 inverse. Getting this. The optimal control law is some gain times this enlarged state Z2. So U in the end equals negative K, can be expressed as negative Kx minus K1 Z1 minus K2 Z2. This is the whole structure of FSLQ problem. Okay? So that will be all for today's lecture.